Hello. Good afternoon. Good afternoon. Thank you. Hold on. Okay, sorry. Hold on. Coming. Okay. Yes, good afternoon. Hold on. Coming. Wait a minute. Okay. Right. Good afternoon, Isabella. Hello, Melissa. Hello, Rachel. Okay, sorry, I'm taking a moment here. And we okay. Uh, coming. Okay. And hello, Ingrid. Okay, awesome. All right, we're coming here. Okay. Okay. Oh, and hello, Tania. Hello, Miles. Hello, Arlene. Hello, Crystal. Hello, Farina, who's beaming in. Okay. Okay. We are going to go straight back to this whole Doppler business that you guys were working on your own yesterday. We're going to find out today what you did or what happened or what. Good afternoon for him. Awesome. Um, yeah, we're going to, hopefully I'll be less spazzy today, although, yeah, well, that's a hope. So the issue today is the Doppler effect. What I want to do today is compare the findings from the 4 different cases. We'll see what, hopefully something happened in those breakout rooms yesterday. Monday, we'll find out. But one item of business first, and that is, yes, okay. So we have the normal, game 50-point class participation thing that happens every class, that you can still take advantage of, you still should take advantage of, you can still retro take advantage of. But I also mentioned, I had been saying that, sorry, I don't know where my head is. Okay, basically, you might have noticed in the Google Classroom, I posted an extra game assignment, so to speak, worth 80 points. This one due by the end of Sunday of this weekend. And even that, of course, all the deadlines are a little bit fluid, but just to sort of clarify or explicate what the most recent thing is in the Google Classroom, it is the 80-point thing in the Google Classroom that says something about FBDs or free body diagrams. What that is the video of the, I think I mentioned this, that it's a video of the class lecture that I gave on free body diagrams to the other section of this course, like in the other 204 section, on Monday, when yes, I did mention it. I started to give them the review or refresher or re-emphasis on the details of free body diagrams, because I think they're super important and they really do permeate the rest of physics for the rest of your physics life and anything that's related to physics. And because a lot of people lost points on something that they might have viewed as very picky or you might have viewed as very technical. People lost points on the free body diagram in the midterm exam. So anyway, so I thought it was worth going over again, but I spent the entire period on it 2 days ago. That was more than I had meant to. So what I'm trying to say is the video from that class, like the video from a class that I did not teach you, the video from the class in the other section, I posted on YouTube, I put in Google Classroom, and I put as an 80-point assignment. What I'm saying is of course, everything is optional really besides exams. You can ignore this entirely, but for 80 points, if you would just watch the video from the other class from any time from now till Sunday, if you just watch the video, and of course I can't, strictly enforce whether you literally watch every minute of it or not or whatever, but if you put some effort into checking out that video and getting something out of it, then just write down one comment or question or indication of something that you got out of the video, or something about, or certainly something that's still confusing you, if such a thing arises. Just give me a sentence or something like, or a screenshot or something about free body diagrams from that video. And if you just give it to me by this Sunday, then that's 80. Oh, and someone else is coming. In addition to the normal 50 points for each day. Okay. So that's just, so hopefully that's sort of clear. That's what I'm trying to say. But it's also a way of saying, like, I can't, and that's a way of getting some points back, like at most you probably lost 2 or 3 points on the exam side. If you get 80 points on a homework assignment, I think proportionally that'll work out. But it's also to say, if anybody's interested in how to do free body diagrams correctly, that explanation is fairly thorough. Okay, but here we're here to get back to the Doppler effect. I gave you an overview of the Doppler effect 2 days ago. Wu has talked about the Doppler effect in lab. I gave you a packet 2 days ago that outlines the various details of the Doppler effect. I don't want to be any more redundant about any of that. I'm hoping that some progress was made in some of the breakout rooms 2 days ago. And I should also make clear, I said to all of you that you were on your own honor, that you could work the way you want to work. And I did deliberately, I absolutely said you did not have to come back and check at the, more people coming, sorry. I absolutely did say we did not have to regroup at the end, or we couldn't really regroup at the end. And there was I wasn't enforcing anything or anything like that. But I also want to make clear that I was there the whole time. I mean, just in case there were questions or there was technical difficulties or whatever, I was there the whole time. So I certainly do know who stayed the whole time and who didn't, I mean, for what it's worth. But I'm hoping that whether you stayed or left, or whether you collaborated with colleagues or not, I am hoping, by giving you all this time and giving you this pack and all this, I'm hoping I'm making it clear that it's really important that one way or another, one way or another, you got to know the Doppler effect. And so what is that? So that's what we're going to sort of find out today. I mean, we're not going to find out in a punitive way, but again, it is on the final exam and all of that. So what am I interested in today? What are we going to regroup and figure out today? Well, and we are going to work together. Like, I will talk and I will answer questions and stuff. But the main summary, or the main, not the intellectual summary, but the organizational academic summary of what I mean when I say Doppler effect is, I mean that there are 4 basic cases, 4 permutations of the same one scenario. The scenario is that either a wave source or a wave receiver has non-zero velocity, has motion relative to the wave medium, right? Like, that's the precondition for a Doppler effect. You have a source, it produces a wave, the wave goes to a receiver. Okay, in the wave will have some frequency as measured by the source, as measured by the receiver. Again, if the source and receiver are both stationary relative to the wave medium, then there nothing interesting or unusual happens, and whatever frequency is measured by the source will be as well measured by the receiver. But if the source or the receiver is moving relative to the medium, so in the case of sound, let's say, if either the source is moving through the air or the receiver is moving through the air, then whatever sound frequency is measured by the source will not be the same as the sound frequency as measured by the receiver. So in common, familiar, everyday terms, what we're talking about here is, right? I mean, that's the situation we're talking about. But That's the whole basic situation, and the whole basic mathematical obligation that we have whenever we're given a Doppler effect scenario is, given the frequency of this wave as measured by the source, can we find out what the frequency will be as measured by the receiver? It will necessarily be different if there's a Doppler effect at all. It will necessarily be the point of the whole thing, is finding the frequency as measured by the receiver. Okay. And I say that there's 4 basic permutations, meaning it could be that the receiver is moving toward the source while the wave is transmitted. It could be that the receiver is moving away from the source. That's 2 cases. Or it could be that the source is moving toward the receiver, or it could mean that, or the source could be moving away from the receiver. There are other complicated variations as well. Like you could have them both moving at different speeds or something like that. You could also have one of them like turning left. I mean, you could expand it to higher dimensions. There are other things that could happen, but the basics of this are these 4 cases: source in, source out, receiver in, receiver out. Okay. And what I'm saying, and I'm going to turn it back to you guys in a minute. I mean, we're going to have like more of a dialogue here, but what I'm saying is that no matter which case you do, the phenomenon or the mathematics of the phenomenon are the same. The approach to solving the mathematics is the same. But if you follow that same mathematical procedure, you will find a different answer for each one of these 4 cases. That's what I want to like share and pair today, is what these 4, how these 4 different cases play out. So, and I really am hoping really to have this be more of a dialogue, maybe even than usual. So I'm, hold on, let me just change the view here. So I'm, okay. So I'm turning to this packet that you have in your possession that you were supposedly working on, that's so rude, that you were working on Monday. I'm going to remind you, I'm turning to page, I think it was, the original problem that we're talking about is, and again, if you're just tuning in now for the first time, like, please find this packet in, like it is in the Google Classroom. But the basic problem we're talking about, well, this is the basic structure of the problem right here, and the basic numbers that I gave you that we're churning through, okay, is here on page 25 of the packet. Okay, this is case 1. Again, I believe it's answered in the packet, and I believe even another case is answered in the packet, but but what I want to find out today, and what you will want to be able to do on the final exam, is you want to be able to do any of the 4 cases here. And again, let me say, or let me try to be clear, when I say 4 cases of a situation, what I mean is, here are the given numbers. In any of the 4 cases we do, not one of these numbers will change. Not one. These are the basic numbers of, in this example of the situation. It's just that how the numbers get applied, or where we put negative signs and positive signs, stuff like that, will vary according to the case that we're doing. So right now, first, we're going to do this case 1, or I'm going to ask you about case 1. So case 1, and also you don't have to like memorize. I'm not asking you to memorize that case 1 means receiver, approach, or it doesn't matter really which case you call what number. It's just you have to understand all 4 cases, and you have to be able to do any one of them, whatever number you call them. All right. So where I left you guys yesterday, where you left me, was first on this example. Now I'm going to ask, like the goal here, like the question is, if so here were the givens, right? Again, it's all about this picture right here. Like this is the picture of the situation. And in fact, this is the basic picture. This picture, in fact, specifically, the way it's drawn right here is, in fact, a picture of case 1, meaning, like, just look at what's drawn in blue for a moment. Like, what's written here is we have a speaker that is sitting still relative to the air, right? It's just sitting there, and sound waves are coming out of it. They're going toward the receiver, which is depicted as like an ear. In this case, the ear the receiver is like zooming toward the speaker. So you want to picture that like maybe that ear is part of a person who's on a motorcycle riding toward the building, playing the music or whatever, right? But in this case, the receiver's coming in toward the source. That's all drawn in blue. But notice then I put a red arrow with a plus sign over it. The red arrow with the plus sign, what am I trying to do there? That is a strategy or decision that I'm making as a problem solver. And I suggest that you make, no matter what case we're doing, what I'm deciding right at the beginning, I'm choosing a coordinate system and saying that whatever direction that wave is going, I'm calling positive. Or more particularly, the direction of the wave as it travels from source to receiver, I'm calling that positive. By the way, I should say, I mean, if this is a true speaker and it's truly making sound, for sure the sound is coming out of the speaker in all directions. I mean, make no mistake, sorry. I don't want to confuse anybody or mislead anybody. I mean, of course, there's like sound coming out of the speaker back here as well. Sound is going everywhere. But the point is, we're not interested in that sound. Like, we're receiving the sound over here where the ear is. So the sound waves that we're looking at are the sound waves that go, by definition, from source to receiver. That direction, I strongly suggest that as a matter of strategy, you always call that direction positive. We might not say anything about that in the final exam, like that, Galileo's principle of relativity, the coordinate system is up to you. And frankly, even if you made that negative, as long as you were explicit and consistent with that decision, you should still be able to solve this problem equivalently, right? So that's why I'm not actually saying that that is objectively positive, but I suggest that you make the direction of the wave positive always, in all cases. In all cases, I suggest that you call the direction of the wave motion as positive, because that way you can say, oh, the speed of sound relative to air is 340, and you can use that number, as opposed to calling it negative 340, which is sort of counterintuitive, and then will generate a lot of negative signs in your analysis that will make a lot of things harder. They should all work out, but they'll make it harder. So, okay, so I'm saying here's our basic situation. And in this basic situation, the givens I gave you were right here. And notice then, by that decision that I just made, as a matter of strategy, I used a red pen to denote that I'm going to call that. So in this case one, where the receiver is going toward the source, if it's going toward the source, that means that the receiver is traveling in the direction that's opposite to that of the wave itself. Therefore, I'm calling it negative 40. Again, that is a decision, right? I'm putting that red negative sign there next to the 40 because of the red positive sign that I put on the prior page, right? Again, a decision that the problem solver is making. And if in some other case, if I have the receiver going in the opposite direction, like receding, then I won't put that negative sign there for whatever it's worth. But anyway, if here's case one, I want to ask, even though I know the answer is in the packet, but if we're solving for the frequency of the wave relative to the receiver, can anybody share in the chat or vocally, did anybody get an answer? I'm partly just seeing if we're all alive here, but could someone tell me, what did you get as an answer for the frequency? And again, just to say explicitly, it says here in the problem, the frequency of the wave as measured by the source, that is FWS. It's a given in this problem that the source sent out a wave whose frequency was measured to be 440 hertz. That means that the source played a middle A on the piano. Like literally, that's what it means. I mean, or honked a horn whose note was the exact equivalent to the middle A on a piano. Like, so in other words, this is realistic numbers. If the source measured her note to be a 440 frequency, a 440 hertz frequency pitch, then can anybody tell me, and you could just tell me the answer, you don't have to tell me, did anybody get an answer? And again, it is in the packet, I think, so you might have just read the packet, but can anybody share an answer for what you got as the frequency of wave as measured by the receiver? Oh, thank you. Oh, thank you. Oh, okay, awesome. Okay. I think the negative sign I might have a pause with, but yes, I love that number. Okay. And thank you very much. And first of all, thank you for like being alive and being human and being with me. And second of all, I think that number is great. And when I say I think that number is great, that's not just like an empty comment. What I mean is, even if I'm not running the calculation even if I can't do all the calculations in my head right now, I like that number that Isabella just put. I think that was a public chat, right? I'm sorry. Wait, that was public, right? Okay, yeah. Can I also say that I like the fact that what she just put in the chat is a full sentence? It's like a complete thought. She's saying like FWR equals blah, blah, blah. Like that's good practice for the final exam too. Like that is a thought that stands on its own. Like it's a complete sentence of mathematics, right? So I also appreciate that. So she's saying the frequency of the wave as measured by the receiver is 494 hertz. It's also the units are correct. Now, I'm going to say right off the bat, like, even if I don't literally remember, even if I'm not looking in the packet, or even if I don't have a calculator in my head, I know that I like that number for two reasons. And to be frank, also, there's one thing about it. I don't actually love the negative signs. I'll address that last. I think that I don't think a frequency, I think I know why she has that there. And so I can get to that last. I think a frequency literally should be I think if we do this strictly correctly, we'll always get positive answers for our frequencies because they really should be like numbers of cycles per second, which really it can't be. But oh, sorry. Oh my God. I am so okay. Wow. You know what? Actually, I'm also really relieved. I was actually surprised. Okay. I'm so bad. I'm a terrible person. And thank you for no, thank you. I actually what I did. Okay. Also, I can't read. Like, oh, and I just lost you. Oh, wait, are you still there? Oh my God, what just happened? Oh, you are still there. Okay. No, that's so my bad. And I'm so glad what is going on with my computer? Hold on. I'm sorry. I'm going to blame this whole thing on my computer. My internet connection is unstable. My personality is also unstable. Okay. No, that's totally my bad reading. That is a tilde, not. Oh, and I love, all right. And that's good. Then I take back any even shred of criticism. Phew. Right. Okay. So frequencies can't be negative, and totally Isabella, of course, knew that. Obviously, who are we kidding? And I like the fact that she put an approximate sign because she is right about that. By the way, that is a cool thing to do. And for everybody, like she's right to put an approximate sign. That makes her answer even more precise. This is something I love about science, by the way. If you precede what you're saying with the word approximate, you're actually being more precise by doing that, because what she's telling us when she puts that approximate sign there is that she chopped off that whatever her calculator said had digits that went on forever, and she chose to chop off the digits at like the third digit level, which is totally the right thing to do. And it's totally right to sort of admit or like announce that fact. So I'm down with that. And I'm so sorry that I thought it was a negative. I'm so mortified. But now, so let me go back to what I was saying before too, then how I know just looking at it, that it's a super reasonable answer, that almost definitely she did do the calculations right, even if I don't remember them, is what I like about that number is, on the one hand, it's in the neighborhood of 440, like it's in the ballpark of 400s. So if she had said something like 700, I'd be like, whoa, I know that can't be right. But also I know, not that it could never be right, but it wouldn't be right with the numbers here. But also I know that it's reasonable and smart because while it's in the neighborhood of 440, it's definitively bigger than 440. And I want to say this right now, because this is where we're going in the class. Like I'm going to check, we're going to see how she did in a second. Either she'll show us or someone else will, she meaning Isabella. But I know intuitively that the answer to this particular case has to be bigger than 440, not because I memorized that it's case one, but because if in this case we had a receiver approaching the wave source as the diagram depicts, then to me, and I don't remember if I said this Monday, to me, we should all, like, one thing you want to know for the final exam is that in a case like this where the receiver's coming in, you should be expecting to get a frequency that's in the ballpark of the original source frequency, but that is definitively higher because we're running into the waves. I may or may not have said on Monday, but this is like if you stood at the beach at Coney Island or Far Rockaway or like Jones Beach if you're suburban. Like if I'm just standing there on the beach, I think I did say this Monday, right? And the waves are coming in like 3 per minute. okay, then they're hitting me 3 every minute. But if Isabella is running toward the very same waves, like we didn't change anything in the water, we didn't change what's producing the waves, whether they came from a rock or a ship or the wind, like the waves are doing whatever the waves are doing relative to the water. Nothing is going to change that. But if Isabella is running in towards them while they're coming, then she's going to encounter them more often, more frequently than I am. And she'll say, no, these waves are not coming in 3. There's like 3.5 per minute, or there's like 4 per minute. And she'll be right from her reference frame, just like I am right from my reference frame, just standing there and having them hit me in the face. If she's running in other words, she will definitely encounter them more frequently. And that's why I'm not surprised by this number. If she were running out, which is another case we do next, then I would expect a number less than 440. So far, I love the number 494. Now, and I do think it's correct. But now, does anybody, whether it's me, whether it's Isabella or anybody else, does anybody want to break down and show? And literally, it could be, either one. Does either Isabella or anybody want to show where that 494 number came from, like how you got it? Or is this an unfair question? Let's see. Okay, maybe it is unfair. Well, actually, maybe that is stupid. But all right, but I think I agree with the number. Oh, and I think actually I do show in the, hold on. Well, let me say this sheet right here in the back is the procedure. This is what I believe we did to get that. This is what I would do every time in every case. And what this procedure says to do. And again, I think I said this Monday, one thing, there is a Doppler effect equation on the web. Like you can literally type in Doppler and you'll get this equation that seems to cover all cases no matter what, and it has like a plus and minus sign in the numerator and a plus and minus sign in the denominator. I'm very aware of that equation, and this is one of my biggest pet peeves. Let me just repeat again for anybody who's ever listening, whether you think it's fair or not, I am telling you right now, I hate that equation. And I love equations. Some of my best friends are equations. I love most equations. That equation is not an equation. It's a formula, and it's a bad formula for a lot of reasons. And even if my reasons are bad, I feel that way. So, someone's here. Sorry. So, like, I am definitely warning everybody. Okay. Oh, cool. Oh, interesting. Okay. No, this is cool. Someone and I see why this is someone in the private chat, so I won't say the name or anything, but someone in the private chat did say that they got the number 498 and they're not sure if that's correct or not. Okay. So I'm about to walk through the procedure my way, and I am warning everybody, whatever way you do these things, don't just plug into that equation on the web. We do design problems on the final exam to make sure that that doesn't happen. You would be doing yourself a disservice if you use that equation that's on the web. Not because you're not allowed to use the web, but that particular equation is corrupt, in my humble opinion. But if we do this correctly, here's a legitimate question. So I'm going to show you how I did it, the way I did it is what's written here on the page in English. But very good question in the private chat, like, because Isabella's already totally admitting, she's saying this is not exact, this is approximate, like I'm chopping off digits, like the calculator did something, and she's right, like that will happen with the calculator. So it's very legitimate for somebody else in the private chat to say, so like how exact or approximate is it? Like if I got 498, is that close enough but no cigar? That's a fair question. Very fair question, because little differences are going to make a difference here in this whole study. So the question is, how little makes a difference? I have to say, we're going to find out in a second. I think certainly if you got 495 or 494 or 493, then that's all the same as far as I'm concerned. If someone got 498 and someone else is getting 494, I suspect that they are doing things two different ways. Like that is just big enough to worry me. So let's find out. I definitely will say this: if someone got 494 in the room and someone else got 498, if you both did it the exact same way, but then it did come to calculator rounding, then no problem. I suspect that that is just a large enough difference that maybe we did it two different ways. So let's find out right now. But that is worth worrying about. Okay, I'll quickly show you. So my way of doing Doppler effect problems, my way that I think captures what's happening conceptually in all four cases, and a way that will show you that you'll get different answers for all four cases, but still because of the same concept. What I do every time is first, I look, and anybody else, by the way, I appreciate. I mean, I've got now at least two people at least two people weighing in on this. The more the merrier, please. Even if you want to do it in private chat, I really want to know. I mean, especially since you had all this time to work the other day, I would really love to know where people are on this. And also, since we are spending so much time, if it's like totally obvious and I'm just boring everybody now, we're going over, I'd like to know that too. So please do like tell me stuff in the chat, even if it's private. I'm about to get Isabel's answer my way, or I think it's Isabel's answer my way, and private chat person's answer. What I do every time, and I'm going to start a fresh. I think this is in the packet, but I'm starting a fresh page now, just for sake of that. Like, sorry. And again, I know it says it's already in the packet, but there's a difference between like a static page and a dynamic lesson. So, and the more you do feel like, yeah, I get it, the good. I mean, if you're bored, that means it's clear. So that's good. I mean, it's not good, but. Okay, so the first thing I'm always going to do in all the cases is I'm going to find the wavelength according to the source, the wavelength as measured by the source, right? The wavelength in the frame of reference of the source. And I'm going to do that by using the frequency as measured by the source, which is a number that's always given, okay? So, there's two equations that permeate the whole Doppler effect. The whole Doppler effect is about V equals lambda F, because that's true of all waves. And it's about VAC equals VAB plus VBC, because that's true of all velocities. It's the two ideas together that are making the Doppler effect. So first I say this, right? That's true of all waves. I'm looking for the wavelength. So I just rearrange it. I'm going to do this every single time, right? But now let me be more specific. I'm looking for the wavelength of the wave according to the source. So in order to do that, I need the velocity of the wavelength according to the source and divide by the frequency of, so I need the velocity of the wave according to the source, and I need to divide by the frequency of the wave according to the source, right? I mean, that seems right. And I'm going to do this every time. But now here's the part where it's easy to skip a step here and still by coincidence get something right, but then never know what to do in the other cases if you're care. I'm going to do this now, right? So I want to plug in numbers for these things. Again, I know this says this in the packet, but like I'm looking for lambda according to the source. So I'm going to plug in V according to the source and divide by F according to the source. The thing to note is, all right, so I'm just rewriting that again. Like I'm looking for I'm just rewriting it. Yeah, I know that this is very redundant for some of you. I can tell. I mean, especially those of you who got answers. Like I know I'm actually saying and writing the exact same thing that I wrote in the packet here, and I almost feel bad about that. And I will try to, I don't want to waste anybody's time, but I also want this to be very clear. So I just note that I know that. Um, um, the big point I want to make right here is we're just about to plug in, yes, like V over F, we're going to get lambda, and that'll be step one of the procedure. And there's only two more steps to the procedure. But the thing to note is we don't know VWS. We certainly do know FWS. It was given as 440 hertz. And again, by the way, like, you know, it may be for some of you, and I also know that some people honestly really did look through the packet and really tried, but maybe are intimidated or confused by all these subscripts everywhere. And maybe those are the people that I'm really talking to the most here. Like I am attempting to clarify this. Anyway, so you got to keep the subscript. The reason there's these subscripts flying everywhere is that we're really, really trying to embrace, acknowledge, and honor the fact that velocity is a relation always. It's never a property of one object. It's a relation between two objects. So all of these things are relations and between any two given reference frames. And the reference frames at hand here are the S for the source, R for the receiver, and M for the medium, to wit, the air. So we know the frequency of the wave as measured by the source, FWS, that's 440 hertz. That's explicitly given in the problem. VWS is not explicitly given in the problem. Like it's not drawn on that page 25 or whatever it is. We don't know it. What we know, like we are not given VWS. We know and this is the whole key of waves. Okay, what we know about a wave is how fast it goes necessarily relative to its medium. In this case, we know that sound travels at 340 meters per second through the air. We do not explicitly know, like not directly anyway, and that's like a law. It has to do that. We spent 3 weeks trying to establish that the wave has to do that, regardless of what the source does or the receiver does. That's what's interesting about waves. That is not true of baseballs or planets or electrons or anything else. Like the wave, the minute it escapes the sources, the minute the wave escapes the source, it's locked into a 340 meters per second propagation rate through the air. Now, what is it doing relative to the source? Apparently, we need that here. We need to know VWS. We were not explicitly told that, and it doesn't have to be 340. Maybe it is 340 in this case, which is why maybe some of you just skipped to that step. Maybe the wave is traveling at 340 meters per second relative to the source, but there's no law that says that that has to be the case. We have to find out what the wave is doing relative to the source. So the way we find out is the one and only other equation that's relevant to this whole process, and that is the Galilean relativity, the GPR form number 4 equation. Like, like the V that we were given, the number we know, 340, that's what the velocity is doing that's the velocity of the wave relative to the medium. That's what we know. What we need here is the velocity of the wave relative to the source. So what we have to do is use the other equation and say, right, this is GPR form number 4. This is the one other equation that's relevant. This is the way velocities work. The velocity of the wave relative to the source is equal to the velocity of the wave relative to the medium plus the velocity of the medium relative to the source. Now, I could have done any combination that works. Like I could also say, just to make this as clear as I can, like I'm using this other principle now, Galileo's principle of relativity. I'm saying velocity of me relative to Earth plus velocity of Earth relative to sun equals velocity of me relative to sun. And I'm saying that's the nature of velocities. That's not the nature of planet Earth or of the sun. It doesn't matter what the objects are. That's just the way velocities work. So I could write down any combination of velocities as long as my subscripts are in the correct order, the correct arrangement, then that statement is true. So I could write down like VWS equals VWZ plus VZS. That would be a true statement. And you might say, well, what's Z? And I would say, I don't know, and I don't care. Like Z could be anything. If Z is a tin cup, then that statement is true. That's the way velocities work. I could just as easily, and if you're like, well, where did Z come into it? Why would you even do that? Well, okay, I could use the objects in the problem. I could say VWM equals VWS plus VSM. That would also be a true statement. Like I just want you to see the pattern of the subscripts. As long as that pattern is fulfilled, then the statement is true. But what I want here is a statement that's true and useful and helpful to the problem. Like those two statements there are examples of truths if they help you understand the velocity concept. But I'm specifically, so if you're wondering like, where did I get this VWS equals VWM plus VMS? Where I got it from is I got it from my ABCs, like pages earlier, but I specifically arranged medium and source and I specifically arranged the medium and source information so that it was both true and helpful. I'm saying like we're looking for, well here, I'll go to the next page. So I'm saying this, and I'm dragging this out as usual, even though we're going to get an answer that might seem obvious to some of you. It's like a lot less obvious in the other cases. So that's sort of why I'm dragging it out. So I'm saying this. And the reason I'm writing it, I'm saying, so let's be careful here. So I'm saying, all right, we're looking for VWS, the velocity of the wave relative to the source. Velocity of the wave relative to the medium, we're given that. That's 340. VMS, also something we're not directly given. No one ever said anything about the velocity of the medium relative to the source. We were not given that, but we were given that the velocity of the source relative to the medium, we were given that number, happens to be 0 in this case, won't always be 0. It's not 0 in 2 of the other cases, but in this case, it is 0. And what we know from Galileo's principle of relativity is that whatever we were given the velocity of the source relative to the medium. And whatever that is has to be the opposite of the velocity of the medium relative to the source. Again, that's an important distinction. Like they're not the same. They're the opposite of each other. Now, in this case, lest I confuse anybody any further, in this case, it happens to be 0. The velocity of the source relative to the medium, here we were told, in this case, the source is sitting still in the air. It's the receiver that's moving through the air. So here in this case, the source was sitting still in the medium at 0 relative to the medium. Therefore, I can infer from that. Sorry. Well, yeah, I mean, yes, but let me just write this better. I'm saying that we were told VSM equals 0. The opposite of that is what is VMS, and the opposite of 0 is 0. So this term will be 0 in this case. So in this case, I'm going to say, therefore, like I'm saying, therefore, here's where approximate starts to come in. So if you do 340 divided by 440 on your calculator, you will have to chop off digits. If you do it to like 3 digits, I think you get 0.771, I think. Hold on, sorry. This is not the final answer. This is just a 0.773, sorry. Okay, now what? Now, I just spent a long time talking about a freaking zero, okay? Which I know a lot, I mean, that seems like a lot to talk about a zero that didn't even make any difference. Like a lot of you might have just put 340 over 440 and got set 0.77 for that wavelength. But I'm being very careful here because in the other two cases, that will not be a zero. And also, we haven't even finished the problem yet. In the rest of this case, you're going to see this exact same procedure reiterate, and there won't be a zero there. So like you have to account for all of these terms. If you're lucky that one of them turns out to be zero, quark bless America. But anyway, so what do I have here? I don't have an answer yet. I am not even in a position yet to check whether Isabella or private chat person like is dead on right or not. I mean, even though I think they both are. What I have here is the wavelength of the sound according to the source. I've now completed what I consider to be step one of the procedure. I mean, it's a long step. It really, I mean, maybe I should call it two, but what did I do to do this step? I'm solving for the wavelength according to the source. And I did it by just doing V equals lambda F and VAC equals VAB plus VBC. I'm acknowledging that we have velocity that is relative, and I'm acknowledging that it applies to a wave, which has a medium. That's what's going on here. So now I have the wavelength according to the source. So then I say step two. Step two is like not even, hello. Okay. Step two. This is like not even a step really mathematically. There's nothing to do here. This is just a step of reasoning. I say, aha, the reason I just went through all of that, the reason I just got the wavelength according to the source is that's the one thing that I think both the source and the receiver will agree on is wavelength. Like again, if I'm standing at the beach next to one of you, or if I'm standing at the beach and one of you is like running toward the water or running away from the water, we're going to disagree on a lot and we're both going to be right. Like our measurements are going to, I'm standing there. I think the waves are traveling at a certain speed relative to me, but you're running away or you're running towards. So you're going to observe that the waves are traveling at a different speed relative to you. Right. And therefore, you're going to get a frequency that is different from the frequency I'm getting. But the one thing we're both going to agree on is the wavelength of those waves. Like they are a certain amount. And yeah, I mean, each crest of all, I don't know, where is my, like the crests of the waves are all a certain amount far apart from each other, and that they're not shrinking or growing while they travel. And I don't care how fast you run into them or run away, they're still that far apart from each other. So this is why I care about wavelength, is it's the one constant in all of this. That's what we're always looking for in physics, is what's the one thing that doesn't change when everything around it seems to change. So I'm going to say, aha, I just got wavelength according to source so that I can realize that's going to be true even according to receiver. So now I go over to the receiver frame of reference. And now So now I'm going to do the exact same thing we just did in reverse. I'm going to do the exact same thing in reverse. Like, what did I first do? I used frequency to get wavelength. How? By using V equals lambda F and using VAC equals VAB plus VBC. Now I'm going to do the exact same thing in reverse. I now have a wavelength. I'm going to use it to get a frequency. It seems like I'm just literally on Y, and it will be the exact same procedure. So this is, I think, why I call this like a three-step thing. Step 1 and step 3 are mirror images of each other. If you really get step 1, you get all the steps for all these cases. But even though it sounds like I'm going to run in circles, like I used a frequency to get a wavelength, now I'm going to use that wavelength to get a frequency. You'd think I'd end up in the same number, but I won't, because the V's will differ. And precisely how the V's differ is where I have to be careful and account for Galileo's principle of relativity. So I say, okay, like, again, V equals lambda F, just like before, but here I'm looking for F, so it's V over lambda, but I'm now looking for F of the wave according to receiver, so I'm going to use the wavelength of the wave according to receiver, so I've got to put in the numerator the velocity of the wave according to the receiver, right? So now I'm at that same stage I was a moment ago, where I say, okay, I'm going to plug in numbers now. I'm going to plug in for the V and plug in the lambda, but I've got to realize that I don't have the V. The V was not explicitly given. Like, again, the velocity of the wave according to the receiver is not explicitly given. So here I'm going to do the exact same thing as before. I'm going to say, in order to get, oh, who's it? Oh, okay. In order to get, so, okay, let me just back up. So we're trying to do this. We're trying to say, VWR is not explicitly given. VWM was. We just went through a whole kit and caboodle, or a whole romp and frolic to get VW something, but that was VWS. Like, that is the way, and it happened. No worries. Thank you. I appreciate it. No worries. But thank you. What was I just going to say? Oh, yeah. So we got to go through that romp and frolic again now. And this time it really is going to be a frolic and a romp. Like, we cannot be careless now. And because there aren't going to be zeros here, and we better follow the same procedure that we sort of just practiced when it had a 0 a second ago. In other words, to get VWR, I'm going to say VWR equals VWM plus VMR. And notice the way I'm writing the subscripts. Like, I'm being careful. I'm writing them out in the order that makes sense. WM plus MR equals WR. There's other combinations, there's other right combinations, but there's a heck of a lot of other wrong combinations. So you have to follow the pattern of AC equals AB plus BC, if that makes any sense. Okay, so now let me see what I know and what I don't, and stuff like this. Like VWM, okay, that's the velocity of the wave relative to the medium, relative to air. So that, yeah, that we know. So that's given. Okay, we're looking for VWR, of course. What we know is VWM is still 340. That's the speed of sound in air. VMR we need. No one ever told us VMR. No one told us. What they told us was how fast the receiver is going relative to the medium. Like, we were told that we were told VRM. This is where you really have to be careful. Again, this is why I'm dragging it out in the steps where it seems unnecessary or seems obvious, is really where you should practice the care here, because what we were told is VRM. Yeah, we were told VRM. We need VMR. So VMR, what it is necessarily is the opposite of VRM. And VRM, if we were careful with negative and positive signs, if you flip back the pages, which I'm not going to do now for fear of throwing everybody off, VRM was negative 40, negative 40. If, assuming that VWM is positive 340, right? Like if the wave is going this way at positive 340, then in this case, the receiver was going against the wave. So the velocity of the receiver relative to the medium was negative 40, right? That was a decision we made in red early if we were careful. And we weren't told the negative sign, but we were told that the receiver was going in toward the wave. So I say the velocity of the receiver relative to medium was negative 40. So we want negative 40 here. And again, you might think I'm crazy. Like I know that a negative times a negative is positive. And we're going to use that fact in a second. But like in order to know what final numbers, I mean, remember there's 4 cases here. So I'm trying to give you a procedure that works for all 4 cases. As long as you are careful and following this, you will know what to do with the negative signs. Again, sidebar, if you just use that equation that's on the web, literally, I mean, it has a plus or minus in the numerator, plus or minus on the denominator, and then it'll tell you like, oh, for this case, put a minus sign here, and then you have to memorize 14 different things of what to do with the plus and minus. And they like, no, it's much harder than this, really. It seems like it isn't, but it is. And then people always get it wrong and they don't understand why it's true. So I'm saying if I'm consistently following the procedure here, VRM was negative 40, therefore VMR is the negative of negative 40. So VMR, oh, in other words, what am I saying in English? I'm sorry. What I'm saying in English then is if the receiver is zooming in toward the wave at 40 meters per second, that means the wave, I'm sorry, if the receiver is like moving through the air at 40 meters per second, like to the west, that means if you're the receiver and you're paying attention, you're seeing air rush toward you at 40 meters per second to the east. Like in effect, the receiver is experiencing wind, right, in the opposite direction. The very reason that when you stick your hand out of the window of a car, you feel wind, even if it's not a windy day, right? It's because your hand is going into the air. Therefore, air is coming into your hand in the opposite direction. So I'm saying, this is still red. Hello. All of which is to say in English, I'm just looking at the time. Okay, we've got 13 minutes. Oh, perfect, perfect. All of which is to say in English then, from the perspective of the receiver, like the sound is not just coming in toward the receiver at 340. The sound is coming into the receiver a lot faster than 340 because the receiver is running in to meet the sound. Like that's what we're saying here in English. And again, if you're truly intuitive about all these things, you could probably guess how the numbers should work without following all these details, but be careful. So we're saying VWR is that. Therefore, back, that's all like the big sidebar to figure out VWR. Therefore, now we can go back and say, like, why did we do all that? Because we were saying, okay, FWR equals VWR over, hello again, over lambda WR. Now we have a VWR to plug in. We plug in 380 meters per second over that wavelength that we figured out in step 1, 0.773, I think it was, meters. And so, and then this becomes that was a rounding thing. So this is approximate. So then approximately and so I get 492 hertz Interestingly, I think that's like right in between what the two people, what Isabella and, or I can't remember exactly what they said, but so I get 492 hertz is the frequency of the wave as measured by the receiver. Now, yeah, and I think Isabella got like 494, and I think someone in the chat got like I can't remember. I'll look back in a second, but this is my answer. I would accept any of those answers. Something right around here is the right answer. I'm clearly chopping off digits. I chopped off digits twice in my calculations, so there is room for this to fluctuate slightly. But and I know I only have 10 minutes left, and I know that this was very redundant for a lot of people, and maybe it went too fast for some people. I'm not sure. But first of all, this is my answer for case one. And it's an answer that's greater than 440. What this, by the way, means is like that if the car played an A, a middle A on the piano, then the person rushing toward the car is hearing like an A sharp. Like this is not high enough to be a B, but it's like higher than an A, if that means anything. It's a little bit higher than 440. If I were going even faster, then this number would be even higher. Okay, but and if I were running away, well. Right. Oh, actually, I'm saying 490. The truth is, if we're going to be this, oh no, I did say 492. Right. Okay. Okay. So one thing I have 10 minutes left, and unfortunately, these 10 minutes are going to be sort of important, or 9 minutes. I'll try not to go over, but they are important. One thing I'm saying as a conjecture, you should check this. If you do the exact same procedure I just did, the exact same procedure with all the exact numbers, but if you change the -40 to a +40, like in other words, if you have the receiver going away at 40 meters per second, I'm conjecturing, I'm guessing, I'm predicting you should get an answer basically like at 388 hertz. Where am I getting that? And you should check, you should make sure that you're doing it right and that I'm not crazy. What I really want to talk about for the next 10 minutes is the slightly less intuitive cases. But what am I saying here? I'm saying if you're thinking that when the receiver goes in the opposite direction, all that should have to flip is a negative sign, that it changes from -40 to +40, you're right. If you're thinking that, you're right. And if you're thinking that the frequency should be lower than 440 if we were running away, you're right. If you're thinking that the frequency should be lower than 440 by pretty much the same amount as it was greater than 440 in the forward case, you're right. Like that's where I just got this conjecture. I'm basically saying that if I ran into the wave and I got a frequency that was like 52 hertz higher than 440, then I think running away from the wave logically, you'd be right to guess. I mean, you still don't have to prove this on the final exam, but I think if you get a number like 388 for the receiver receding case, you'd be right. And we're both on the same page. But with the 10 minutes I have left, what I really want to emphasize now is, okay, and so please check. You should check for your own, both check that I'm not crazy, but also check that you know what you're doing. But the real thing I want to talk about right now that I'm not sure is in the packet, it may or may not be. Oh, I didn't mean to do that. Yeah. Now, again, I don't care what case you call number one or number, I'm probably not even being consistent. which one I call 1 or 2 or 3. That's not the issue. The issue is, let's, for the remaining time of 7 minutes, let's think about for a second, what if the source approaches at 40 meters per second? And this, again, in theory, I was asking you all to do 2 days ago. I don't know how much time you had or whatever, but, and you definitely need to do this for the final exam. Here's the thing, like, so the picture I'm talking about, all the same numbers, right? All the same numbers, all the same facts. But this time we're saying, like, this time the source is moving and the receiver is just sitting still. Like, the receiver is sitting still in the medium, 0 meters per second. But now we have a source that's moving relative to the medium at 40 meters per second again. And I'm going to say positive because I'm calling the direction of the wave positive, right? So now it's a source. Now, look at that for a second. We have 6 minutes. Look at that for a second. All the numbers are the same and the relationship is the same. Like, again, except we're having a squeeze in situation, not a spread out situation. This would be akin to if you were standing at the beach, like we're at the beach, waves are coming in, and let's say the waves are being formed by some boat that's causing those waves, or we're at a pond and ripples are coming in because of some rock that got dropped into the pond. What I'm saying now is, imagine that the boat is moving in toward us, or the rock is moving in toward us while it makes these waves and moving in at 40 meters per second relative to the medium. On the one hand, I conjecture that, again, here we're having a squeeze in situation. So I do expect, and it is correct for me to expect, that if once again, and assume again that the frequency of the wave as measured by the source is again 440 hertz, like assume all the same numbers again, and assume that the velocity of the wave according to the medium is 340. If this time it's the source moving toward the receiver rather than the receiver moving toward the source, I think the logic or the concept, the visual picture should be the same. I think we should expect that the solve for frequency, I think the solve for frequency as according to the receiver will again be greater than the frequency according to the source. Like, if you're expecting that, I think you're right. And if you're not expecting anything, you need to think about it. But again, we're having a squeeze in thing. I think if the source is moving toward the receiver with into the waves, we're gonna hit those waves more frequently than otherwise. But I do not think we're going to get the same number as we did in case one. Okay. And this is an interesting point. Like, relativity is relativity. I move to you is supposed to mean the same thing as you move to me. But here we have a medium involved. So I think we're going to get the same type of change, but not the same change. So with 4 minutes. So I think the answer to this question, to this case, should be a number that's greater than 440, but should not be the same as Isabella's or private chat person's number. It should not this time be 492 or whatever. And you'll really know you're doing things right if you, so I'm going to quickly show, so I'm going to show you why we're going to get a different number, but even with the same procedure. So what I'm going to do now is, because there's only 3 minutes, I'm going to literally write out the same procedures I just did, but I'm not going to talk it. I'm just going to write it, and you should, okay, and then all the same would be for source receding with negative. Anyway, I'm going to write it, and please see what but in the end of the day, you'll know you really understand the Doppler effect if you can understand why source coming toward receiver will not give you the same frequency as receiver coming toward source, even though you will solve for that frequency by the exact same method. So here we go. And again, I'll try to just write it without talking because I know we have 2.5 minutes. I'm going to do it faster this time, but
So you notice it's doing the same procedure, but already right from the start, there's no zero in the top there, right? And there's a negative sign. Okay, so this is the wavelength. Then I go to the next page. Again, I'm going to put this packet in. Of course, I'm going to put this packet in your stream, but next page. Okay, it's 420. I did that very quick, but I'm just note, I just got another number that is higher than 440, but it's not 492 or 496. It's 499, but these are small differences, right? But that is just big. That's a different number, 499. It's almost 500. Why did I get a different number? Because in this case, the actual wavelength that, like in the first case, we sent a regular everyday wavelength, but it was received at a faster speed. Here, we sent a smaller wavelength that was received at an expected speed. You need to think that through. We'll talk more about it Monday, but and then what would be the answer for case 4 would be like 399. Like it'd be it'd be 390. It would be 440 minus 49 rather than 440 plus. But you have to see how the different cases all have the same procedure but get different numbers. That's all. It's 420. Thank you for being so patient. Sorry I'm yelling so much. That's the Doppler Effect. Have a lovely day. And thank you guys for participating. Okay, thank you. I appreciate it. Thank you. Thank you. Thank you both. Yes, thank you for real. Okay, I'm going to shut up. Good. Thank you. Awesome. Good. Bye.